Let me put it in the record actually. Yeah, fantastic. So today, there was a wonderful topic which you are going to presented by Dr. Haran is structural dynamics. I believe there are a lot of photographs. There's been kept it for a more an understandable manner, and he will give you in detail about the structural dynamics and to be an understanding of what we have discussed in the class, just for the glance, time period and base shear and moment, and all those things. You will get it in a very clear idea. Dr. Haran, can you able to hear my voice, right?
Yes, yes, sir. Thank you, sir. Thank you for
Fantastic.
introduction.
It's my pleasure. Yeah, please move on. Dr. Haran, because people has joined, on waiting here for more than 10 minutes. So we don't want to delay. Please carry on, because anyhow the session is recorded. So let them join. Whoever want to join, they will join it. It's fine. Yeah, please.
Yes, sir. Sir, I shared the screen. Can everyone see the screen now?
We can able to see the screen.
Yeah, yeah. Fine, sir. Fine, sir. Thank you, sir. Yeah, I'm welcoming you all for this introduction to structural dynamics lecture. We just see why. First, we will cover why it's structural dynamics is important for the buildings. Why this analysis is important for the buildings. Then I will jump into the basic introduction. What all the basic things required. How to do small analysis. What are the parameters required. Uh, I'll just show you some building. So this is normal buildings. What we see here, people are living here. These buildings are designed as per codes. So if it is in India, they follow India codes. If it is in USA or in UAE, or they follow their own code. So there is nothing problem with this building. So this is what we will think. So once I think after the end of the session, maybe I'll ask you what all the problems can we identify just by this one picture. I'll just go to the next slide. So these all are also similar kind of buildings where architecture is given more importance for the building. One, we can say this is like a cantilever type, or we can sometime we can say floating column type, but this will come like a more like a cantilever structure. So here the importance is given more on architecture point of view, and of course they will calculate how much the seismic load will come. Based upon that, all the maybe the dimensions, structural dimensions will be higher. Let's jump directly to what happened in the previous earthquake. We can see this building is actually Burj, what is that? Gujarat earthquake in 2004. So this building has been collapsed. We can see that the above the buildings are standing, where only the ground story has been failed. Similarly, there are other kind of case where we can see here the ground story column is failed. We can see the column dimensions are just 230 by 230 or 300 by 300. There is no special care has been given to the columns. The building is standing. Similarly, here in this second picture, we can see the column is there because of the window opening. The column, this kind of failure they normally call short column failure, because the more drift this has to take more drift. Drift ratio we can call. Drift ratio means it's a horizontal displacement or divided by the height of the story. Also this kind of problem can also happen because of the windows. So here in this picture, this again some kind of damage we can see in this column, particularly in this column. This kind of failure is mostly depending upon the more torque on the building, more rotation kind of failure. And again, this we just saw in the above. These are all some of the failures we saw. Hi sir, is everyone okay now so far?
It's audible, sir. Please go ahead. Actually, for
Yeah,
everyone is okay, right?
Yes.
yeah.
Yeah, it's
Fantastic. Yeah.
okay.
Uh, yeah. So what we saw is there is a building so far. It's fully occupants. People are staying. Everything is fine. And then we just saw like a glimpse of how the buildings were behaved in the past earthquake. Now, in actually what is happening is we are modeling the structural, only the structural elements are modeled. We are analyzing it. We are finding its axial load, how much coming, shear force, how much coming, and moment is how much is coming. These are the main things we are checking. And also the secondary effects, due to secondary effect, how much additional moment develop, additional torsion develop. So this part only we are doing in analysis part. So analysis part we are just doing all the loads we apply, and then it comes based upon the assumed load and the results from the software. We are designing, we have the formula for moment. If moment is this much, we calculate the dimension and the reinforcement required. Similarly, based upon the shear force, we do this. So this is okay, we are following it in construction point of view. But this is not going to look really as it is. We will have an infill wall. We have some windows are there. The loads, all the loads will be considered. So in construction practice, it's different. So this particularly I just pointed out here. In most of the buildings we have infill walls in the ground story also. So here I took some particular case where there is a possibility that in ground story they will not use infill wall, which means this space they use for some function. For example, mostly in a densely populated area, they use this for car parkings. So they just use for car parking. So this has an highly functional, more important, they try to give more important this kind of building. What happen is, we all know that horizontal force, the seismic force is horizontal. So when the horizontal force is applied, when the infill walls are present, the loads are transferred in the diagonal strut form. If the infill wall, if this diagonal strut is not there, the load will be, this horizontal load will be more, will be taken by this column in the form of shear force and in the form of moment. But what happens to this infill wall? The infill wall actually have less strength. It's not the high strength. If you saw something like this, if infill wall is not there, the column will be able to take some graph like this is delta and this is my P. But this infill wall, because of this infill wall, my initial stiffness is going to be so high. My initial stiffness is going to be so high, and at this point, my infill wall is collapsed. Then again, it will come and follow the same path. So this is just an example. We just understand now. This infill wall also takes some amount of load for a small displacement, because for small. So now we'll come back to this three form. This is what our analysis model, we say or we assume all code provisions except for this. When horizontal load applied, the loads are transferred using columns, acts like a shear force, and the moment is developed. So this is a moment resisting frame. In case of fully infilled frames, initially for some time the load is transferred till the so this looks like more conservative. Even though if we are not considering the infill wall stiffness, this building is going to be more safe. And also there are practical problems are there why they are not considering the infill wall stiffness is because the brick, there are different n number of varieties of brick available. The bricks compressive strength ranges from 2 newton per mm square to 8 newton per mm square. First class brick, second class brick. Here we are using hollow blocks, and hollow block itself different ratio. So we cannot able to standardize it when in the during the design stage. But when we are going to check for the performance, at the time we will be adding it. We will see later stage what is performance. So now we'll say this is conservative compared to our design stage. Now what happens, suppose in this kind of building, in the case of OGS building, which means there is no infill wall, so the loads are transferred here suddenly like a infill strut model, and here the moment model is coming. So in this case, what has happened is the more shear force is developed for the ground story, so it cannot able to resist. So this is a special case. If it is an OGS building, we need to consider the infill wall stiffness also. And now the code has been given, the code has given some clause that we need to maintain something, either whatever the design moment is coming here, we need to increase the design moment. Each code gives different value. We'll see what ASC code is giving. For this kind, we can say soft story building. In analysis time, this is not a soft story building. So this is not a soft during analysis time. But this is not a soft. But during my construction time, then this behaves like a soft story building. They call it as an inverted pendulum kind. Then I'll just jump directly to shear wall configuration. This is our general building frame. I'm just from the top view. Now, the shear wall can be placed in the external walls and the internal walls, maybe like an internal core member, or maybe one side. Maybe they feel this side only seismically it is weak, this side it is heavy, because maybe they make a column is bigger or something, so they may provide only one side. They put two separate, on another is like a combined structure wall. So which one we will choose? So this is also again a question. Which one is perfect? All are same shear wall. We get from analysis we get a base shear value. So for the base shear value in x-axis or in y-axis, we can choose. Now here, which one will govern the location is, it depends upon the torsional, like mass irregularity we call, stiffness irregularity will call. Now in this another thing you can see, all this are symmetrically placed. In terms of stiffness, now all are symmetrically placed. Which one is more good? So again we need to do some research and then we have to come to conclusion which one. And mostly what we found is, they found this kind is mostly perfect. This gives more good. Again, what the problem here is, there is some small gap is there. Because of this gap, this beam will be subjected to more secondary force. So most probably they will prefer this one. Otherwise here they have to go for thicker beam in terms of torsional point of view. So here they will go for the, so in this case this will not come. So it's like a full of rigid member. It takes how much torsional value is coming. Based upon that they give the reinforcement. This is totally avoided. This will create like a torsional, more torsion. The building will twist like this, or during the seismic, even though my seismic is perfectly x-axis, because of this unsymmetrical stiffness location, my building will be shift like a torsional behavior will come. So this is okay, but only one side they are considering. We'll come back again. Just I am giving idea how the shear wall is also one of the main parameter we need to consider, and its location. Not only shear wall, we can use some bracing systems also. There are different kind of bracings available. So which one will use? No, normally this will be preferred. They will not go for this because the load applied here will develop here a more force. So this beam will be subjected to suddenly more point load. So this kind will be not preferred. This is also not preferred. They say this is very good, and this is also very good, because when my load is applied, the horizontal load is distributed only to this strut, like a diagonal element. So this member is also not allowed. Not they are not using this kind for seismic behavior, because when the horizontal load is applied, the load from here it is transferred to this column. So this column is suddenly subjected to a, like if it is like a beam column element, it will be subjected to more point load here. So we can construct anything, any method we can construct, but we need to choose which one is optimum, which one will give my column section very less, reinforcement section very less. So mostly in this configuration they go for this two method. Now we do some comparison. This is again building from the plan. We use global braces only on the outer periphery, and the shear wall is there. In the I didn't share that. Okay, actually in the elevation. So this building, in the elevation it may be look like this. Okay, let's say in periphery we model this one, global bracing. We model this global bracing here, and here it is the shear wall system. So shear wall is probably this shear wall system we modeled. Then we apply the lateral load. We will apply the lateral load, and we will check if there, we will compare how the bending moments are developed. If there is no if there is no shear wall or anything, you can see here the bending. This is moment resisting frame. This is a moment resisting frame where you can see the moment is in the ground story is more high, and it's like gradually increasing from the top to the bottom, because all the moments will be taken by all the nodes, all the joints, and then it will be transferred. In case of global brace, subjected to the horizontal load, which is equal to seismic load, the seismic load is completely taken by this bracing. They also design this bracing like to take only the axial or tension. Not, they will design this global bracing such that it will not take the moment. It will take only the axial load. So in that way they design. So the moment is drastically reduced in case of global bracing. In the case of, so here you can see the global bracing system. So similarly, in case of shear wall, so the moment is developed on the columns. In the columns, the moments are developed high. In the shear wall also moments are developed, but the shear wall is able to take this moment. But the thing is, the adjacent to this building column also we need to consider. But in the case of global bracing system, the moments are not heavy. All this building we apply the same amount of horizontal load. So from this we can conclude that only with this there are so much is there, we can conclude global brace is good from the analysis point of view. In the point of construction point of view, we have to see how we join. Suppose the building is an RCC member, how do we join this steel member here? You cannot make this as a concrete member, because that will impose additional weight, connection, construction point of view more difficult. So in construction point of view, they go structural wall is easier. It again depends upon the money, it again depends upon the location, it again depends upon the availability of material and the construction time for the project. So it's all govern everything, which one is better. So from here we can come to conclusion, we can use global brace also, we can use structural wall also, but the global brace system is drastically reducing by the column demand. Similarly, in case of shear force, if we compare the same building with the shear force, we can say moment resisting frame has a shear force is drastically increasing as we go down, because we have all the horizontal forces here. All these forces has to take from by this foundation. So ground story will have a more shear. In case of global brace, all the forces are taken by this bracing system. The shear force developed is less. And here the structural system will take the shear force, and each story also will have a corresponding shear forces. This shear forces, what we see, all these are developed due to the individual mass. Each column will be associated with individual mass, effective mass. This mass will generate the horizontal force. Uh, Now axial force, the same problem, we go to the axial force. Axial force is the main for a column design. As you see this in the moment resisting frame, the ground story column has to be designed for heavy axial load. In case of shear wall system also, we need to design for, because my building system away from this, suppose you take this column, all this load will come to this column. So the axial load to this column in case of shear wall system is going to be high. It is same here also. It is the same here also. It all will come here only. But we are just showing this frame. With this frame, we are just showing you only this frame part. We are just showing. So here this column will have maximum load. This column will have this part of the load. Axial load will be more here. So here also the load will come to this column as well. Some part will go to the shear wall as well. But for the simplicity of design, we will not use this P for this. We assume all the P it goes to this column, the axial load, in case of our design. But in actual, it's different. So that is the next step. In performance based, we will go for that. So whatever we are doing analysis is a force based design. So we'll come back here. We will see here that the demand here is reduced. In moment resisting frame, the demand is high. Similarly for shear force and axial force. So this is very important to understand. So bracing and shear force. I'll just go to the another concept, floating columns. What happened? We just model this floating column. Floating column means the column is coming from top story, but suddenly there is no column here. It is like a overhang. If it is like a overhang, what happens suddenly? If it is overhang, the demand the demand in the ground story column is going to be more high. Suddenly it is going to be more high, and my shear force is also going to be more high. So if you are designing this kind of building considering the seismic effect, if for axial load it is easy, but if you are considering this seismic horizontal load, you need to increase this column size drastically and reinforcement drastically, then only the building will save. All otherwise the building will collapse more easily under seismic load. So for floating column, as much as possible we have to avoid the floating column, but the architect will come with innovative design, and for some kind of project we need to consider the floating column, because all the projects aesthetic is very important. We have to say, people likes to say wow, than the safety. Big people are not aware of the safety point of view, only engineers knows. Only we are only afraid of safety. So in this kind of building, if this is compulsory required, we need to consider the effect of what is going to happen here, how much we need to increase. Then this is again a very major problem. In every country, an architect and engineers will fight for this. Buildings on grid and buildings are not on the grid. So this is an example, building B, where my all the columns are in the like a graph sheet. My all the columns are exactly in the node, and this room will be used for one purpose, another beam will be used for other purpose. This dotted lines are our secondary beam. Here for construction, so they don't like to use secondary beam here. Depending upon the serviceability, they use the column in irregular shape. In UAE this is most common. In UAE most common, we are not able to construct this kind of building at all, because of accessibility, because of feasibility, usage of the problem, we are not able to use this. But this kind of building is highly recommended for seismic effect, because this kind of building will not give you additional torsion due to seismic. Because of this unsymmetry, if suppose let's say my earthquake is happening in x direction, in this direction, this building will go in this axis only. Let's assume all other stiffness are same, masses are same, but in this building even stiffness and masses are same. Even for the horizontal building, because of this different on grid, this building will behave like torsion. The building will undergo torsional effect. So the column, when we are designing this column, you need to provide more reinforcement considering the torsional effect, whereas in this case you no need to increase the reinforcement or the column size. uh, so let's take this frame. Let's take this frame and we apply the horizontal load. You can see here, this column, probably this column is subjected to more axial force, and here also axial force is increasing. This is normal. Axial force is not a problem, because this column is going to this much load will come to this column, and this much load will come to this column similarly. So axial load is not a big deal. So when we come to the shear force, what is this shear force? So in this building, the shear force demand is same in all the column. So all the columns are, so this both columns will have same, and this column and this column's shear force will be same. And here you see, because of this uncertainty, the grid on grid location, suddenly this column has more and this column has very less. Probably this column, which one? I think here no column. Huh? No, 1, 2, 3, 4. Yeah. So this column is this column here. Okay, it's very less. So here, the same uniform size of the column will not work out. You need to make this column should be bigger. Only considering the shear force. Because of the shear force alone, you get the more high demand for V. You need to increase the column size, and this will make our structure stiffness irregularity. So this kind of building will provide more stiffness irregularity in the building. Similarly on bending moment, so here you can see the bending moments are almost same in all the columns in the ground story. So here the bending moments are not same. Here the bending moment is not same. So this is also another problem. Next, I'll go to structural wall discontinuity. So whenever we construct a shear wall, if we stop the shear wall at some story, this adjacent story will have a more drift demand. So drift demand is, let's say, displacement demand. So this demand will be suddenly more. If you stop at this location, here you will get more displacement. This part will be safe, but this above part will be have a problem. As you go up, let's say this part is fine because my mass acting here is only this much amount of mass is going to come. This four columns will be enough to take the mass, but when we come to here, it will be the mass of this plus mass of this floor. It will be taken by this shear force. So now, based upon this analysis, all this should be avoided. We should not use this kind of shear wall at all. We need to use this shear wall. I guess everybody knows this part. Huh? It's just like I'm giving, even if you know, just I'm going through the basics. Huh? Uh, so now this shear wall, why this is not good? They just go through here. Let's see. Say this is which one? It's like shear wall, shear demand, and this is your shear. This shear demand. If you use the shear wall here, this all the story shear force will be taken by this shear wall, but the above story your shear wall demand is high. Similarly, let's take this column. You get the above story here. The shear load is more. Shear demand is more. You get here more displacement, more drift. We call drift here. When
Dr. Haran, your voice is disconnected. I mean, can you just come closer to mic?
load, no, some later load we apply. How much force, how much moment is we are just checking it. So similarly, in this case also, the bending moment is developed here due
Is it, can you able to hear
the
Dr. Haran
building plan.
voice?
Everyone will go and we will consider drift demand. Long column, for example, this column.
Recording in progress.
So this column 20 mm. Let's say let's say 50 mm. Let's say 50 mm displacement before going, but this column will get failure because of this staircase in the building. So we need to consider dog leg. This is called dog leg staircase. To provide this, or we need to avoid touching the column. We need to think about case called the stiffness irregularity. OGS building we already discussed. In some building, what they do for architecture point of view, like a glazed structure. So there will be no infill wall. But up and down, there will be an infill wall. So this building will be very good. But here, the because of the infill wall stiffness. And here we have a columns is very high, and here we say column is less. So this kind of problem also should be avoided in case of SIG design. Normally, when building is obviously bottom story will have a high shear force, axial force. So our size will be higher. Here we will have a less axial force. Our section will be less. So, but what we have to do is we should not reduce the cross section of the dimension as much as possible. possible, we may slightly reduce the reinforcement and make my moment of inertia as much as equal. Also, buildings on the slope, I don't want to go here. Obviously, here we'll have a large axial force. This will induce large bending moment and large shear force. We need to consider this difference also. This is another important parameter in seismic effect. The build descent. This building will have a different time period. This building will have a different time period. Both building is not going to stay together like a railway track. It will not behave same. It will behave different, obviously. So when it is shaking, this part it will get damaged. So normally in all our buildings we use temperature thermal expansion. So we use thermal expansion is must. So on that case you use thermal expansion, but what happened to the building? Sorry, just 2 minutes. I'll just drink water. So this is effect. So we need to consider this due to seismic. What is going to happen? How much allowable is going? How much reflection is allowed? Sorry. So how much gap is required? Or do I need to design continuously for thermal, considering the thermal effect, considering the thermal stress? I need to design the building. This is also on the question mark. Which one to choose? Similarly, building height difference. So now I have a question for you all now. So this is a building now. This card. Now, do you find any problem in this building now? Can you say something? Anyone? Or it's okay. Are you following me or just like boring?
So we are with you, but the problem is your screen has gone. I mean, could you please reconnect your screen? I mean, the
Now gone,
sharing
sir.
PPT has
Yeah,
gone.
yeah.
I mean.
Now wantedly I made. Sorry, this one not. Yeah, yeah, yeah. So you are able to follow me now, sir. You feel like a boring session or how it is?
No, 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 at all, actually, at all. I mean, it's fantastic. I mean, like, you are going with the basics. I mean, that's good, actually. This is what we are expecting, such kind of brainstorming questions. I mean, like, yes, what is the question? I mean, please go ahead, actually. Then I will
Sir,
start with
yeah.
the interaction. Then people will follow me, please.
So, yes, sir. Now I need some answer from you. We saw this building. This building is
Correct.
designed according to the code for their country. People are
Excellent.
living
Okay.
here. So now
Okay.
can you identify any problem in this building
I
considering to
would
seismic?
say,
Sorry.
the before slide, the one which you saw, the ground floor, it is all like, longer column, which is slender column, actually, So the first one is slender column
Yeah.
at
So
the
one
ground floor. I
problem
mean,
here,
yeah,
sir.
yeah. And the second is, I would say, like, there is a cantilever also is there, actually, there is a
Sir,
cantilever in both the end. I can see this.
true.
Yeah,
Correct, sir. Correct. Yes.
please
Yeah. So
go
there,
ahead
yes,
with
more
your
slab.
answers, please. Yeah, please go ahead with the answers. I mean, yeah. Mr. Suresh, Farzana, Mebin, and Abu. Okay.
Uh,
Yeah,
Yeah.
please.
Show staircase. The windows, but Wogluck staircase, if you could explain one more time.
This case, in this case, when we apply this load, it's not free to move from here. It is free to it will deflect from here because this slab is holding it. This slab horizontal rigidity is high. My horizontal stiffness is high. So here it will stop, like it will stop. My beam will deflect in this side. We have this drift. Now you can ask, what is the problem? What is the problem here is, they say here, I'll just oh, sorry, it gone, right? It's okay. It's okay. I'll just do it again here. Let's say this is my column. This is my another column. So here, so these are the this is, let's say, yeah. So if for this horizontal load, let's say this is my horizontal load. So in this case, my building will deflect in this path. So here what I have is, here I have, let's say drift is 50 mm, and this column height, let's say this column height is 3 meter. So here my column height will be reduced to 1.5 meter. So this is also 1.5 meter. So in this case, this will be deflected in this region. This will deflect in this path. It will not say 50 mm. Let's say delta. Let's say x mm. So normally what happens is, this column will get failure. Let's say at 50 mm it get failure. There is a formula called drift ratio. My drift ratio is equal to drift ratio is equal to, I like drift divided by height of the story. I put height of the story, so I'll call it at a story drift ratio. So this is my formula. Usually this value, we have some performance limit. This value is 1%, varies from 2 4% depending upon performance limit. When I say 1% means this is my limit. Let's assume now 1% is my limit. Okay. If I say my drift is 1%, how much for, let's say this is now 50 mm. Now this is also, let's say 50 mm, it's deflected. What is our formula? Drift divided by height of the story, which is 3000 mm. So since I'm saying in percentage, I'll multiply by 100. So I'll come here, 50 divided by 3000 into 100. So my drift is coming here. This one, first one I'm getting here, 1.7 percentage. So my drift is 1.7 percentage here. Okay, but in this case, when we see to this problem, it will be 50, but my dimension is 1500 into 100. So it will come exactly divide by 2 into 2. So I'll get here 3.33 percentage, my drift ratio. Let's say 4% is near to collapse. My 1% is fine. Is called so if my building is like collapse point, let's say my drift limit is not, this is not according to the code, this is according to some performance limit. So my building will collapse if the column is deflected for a 4% drift. This is my this is what the general rule. So if my column is high for the 50 mm, my demand is coming 1.7 percentage only. But for the same 50 mm, because of this 1.5 meter height, my demand is increased to 3.33 percentage. So this, if further it is increased to 60 mm, here also 60 mm, but here it is safe, but here it is not safe because of this short column effect. Fine, sir.
Yeah, that's clear.
Clear, somewhat okay. Thank you, sir. Thank you for. If any questions, please welcome. I'm happy. Um, so we'll go back to our basic terminology. I'll just make this full screen. Uh, we'll go from starting. The from starting, what is displacement? We call it a deflection. Deflection is how much is moved from the prior moved from the my previous place. Is we usually measure this is in or meter in SI units. Now, what is velocity? Velocity is our distance by time. And what is our acceleration? It's velocity by time. Rate of change of velocity by time. This is our general formula we know. Why we want to understand this is because we are going to deal with the dynamic. Dynamic means the object is moving. In previous case, we solved something, everything is a static. My force is equal to K times delta. Here, if my object is moving, it is dynamic equilibrium. My object is moving. It has some velocity. It has some acceleration. So we need to consider, first we need to understand what is acceleration, velocity, displacement. The next terminology will go for a time period and amplitude. Let's take one building. We just attach with this, we initiate the building, and then we initiate this building. This building is moved for, let's say, some displacement. Let's displaced for delta. So this point is moved for some delta displacement. Then we cut this wire. If we cut this wire, this building will vibrate. This building will vibrate left, right, left, right. It keeps on going. And after some time, it comes to the rest. So that displacement, we can plot it here, okay? We plot it like a graph. So this x-axis is your time now, and your y-axis is your delta. Did you understood this graph? How we got this graph? Because my building is moving left right with, and each cycle it is reducing because of some damping. We'll come to that one point. Now, what is my time period is to complete one oscillation, how much time it took. Let's say it starts from, we'll make the clock on. We start from here, it goes here, it comes back here. How much time it takes? Or we can start from here also. We start from here. This is my one cycle. What is the beauty of this dynamic is your displacement will change, your time period will not change here. The first cycle, second cycle, third cycle, your time period will not change even after your amplitude is decreasing. So this vertical height is called amplitude. So the vertical height is called amplitude. So time period. So everyone knows now what is the meaning of time period. I think last class I explained. Most of them already know about time period. Amplitude is, amplitude has a unit. Okay. So this amplitude may be in or something. Now the same graph we can plot it in terms of velocity versus time, in terms of acceleration wise time. Whatever you do, you get the same time period. Time period is not going to change whatever plot you do, because this beam is moving, building is moving, it has a displacement. We can measure the velocity also, we can measure the acceleration also. uh, so I just go to next slide. Let's see what is time period. Now let's take a different buildings, small building, high building. This, let us assume I am giving some force on the ground story. Let's take, I'm pulling this with a train. So train is pulling, it goes some horizontal motion, it's moving in some constant velocity. Obviously the load here also some velocity will happen. What the point we need to understand here is, I just simplified this to different single degrees of freedom. So each system will behave differently. Each system will behave or deflect differently, depends upon your building time period. So building time period, mathematically they come to one formula, which is mass and K. Mass is the mass of this one, K is the stiffness. So another important thing what we are have to understand here is, all my time period I am using it only in X direction. Okay, so I'm finding only in X direction. uh, Obviously in other direction also something will happen, vertical direction also something will happen, we will ignore all this. My intention is, my earthquake is in X direction. Now I will find the effects only in the X direction. So normally we call this is a time period. Time period is 2 pi by root of m by k, mathematically formula. They also call as 1 by f. Time period is 1 by f. So what is frequency? I'll come back here again. What is frequency? Frequency is number of cycles per time. So in 1 second, how much cycle happen? In 1 second, one cycle or two cycle or 2.5 cycle, 1.7 cycle. So this figure is an example. This figure is an example that a different frequency can happen. What is natural frequency? So natural frequency is again okay, frequency, there is two term, natural frequency. Actually I have another slide to explain about natural frequency. So right now natural frequency is 1 by time. It will be measured in 1 by seconds, or simply we can call it as a hertz. Now I'll come back to this time period problem. Let us we model this in ETAPS, different building height, and we found what is the fundamental first time period. Let's go to this x-axis. So each building, you see, when the building is increasing, your natural fundamental time period is also increasing, which is your black in x direction. Similarly, in y direction, y direction is this axis. Y direction is also is less or similar. It depends upon the building configuration. Here we use all symmetrical building. Okay, and also we found torsional frequency. Yeah, so rotational frequency. When we solve the analysis, it will throw us the result. We have nothing new here. Just we analyze, we see the mode shape. If the building, if it is deflecting in this axis, like in this manner, it's bending frequency, your first frequency in x-axis. If in the top, if my building is mode shape is rotating in this axis, twisting, then we call it as a torsional mode shape. Corresponding to that mode shape, we will find what is the frequency, and that frequency has a natural time period. So here I just show just the variation of different height of the building. This all the actual time period. Our code book also have a typical formula. We use the empirical formula, we will get almost similar. Now frequency is another important. They call it as a, here we measure for 1 second for one complete cycle. How much it starts from here to here. But in case of angular frequency, they make how much theta, how much angle it is deflected divided by time. Okay, so here this you can type angular frequency in the Google. Wikipedia have this drawing. You can go and check. This is the relation between the radians and hertz. So we can say here radians is one complete cycle is 3.14 radians. Okay, 3.14 radians, or we can also say 2 pi of radians. Pi is 180 we call. Sorry, pi is 180. This is 2 pi. One cycle is 2 pi. Pi is 3.14. Will not confuse you here much. We measure how much degree per time. Normally we will not measure it in degree, we measure it in radians. So we will not use degree at all, 180 degree, 280 degree. We will use, so that's why it's coming 2 pi divided by time. We get it in radians. So in general, directly if you are using K and M, we get the answer result in radians per second. This is all angular frequency. Natural frequency. So natural frequency, again I will push this to the last slide. We'll come back there from there to here. So these parameters are very important in dynamics. I'll come back again. Amplitude is okay. Time period, frequency, angular frequency, natural frequency. We'll see that later. So then next comes accelerogram. So accelerogram is an instrument actually which shows our accelerogram plot. It gives us x-axis accelerogram will plot x-axis time, y-axis acceleration or displacement. We can convert, if you differentiate, integrate acceleration, we get velocity, integrate again velocity, we get displacement. So these are the different earthquakes. Okay, this is in acceleration format. You can see here high, less. This earthquake has a very high time period, time duration is very high. Here initially very small, then suddenly high. Now what this each ground motion say us is, from each ground motion we can find what is peak amplitude, what is the duration, how much, what is the ground shaking, how much frequency content are there inside, etc. What is the what is we call areas intensity, how much, what is the significant duration. All these are different parameters. When we go more into the accelerogram, we will find all this. But for us, there are two things are important, which is called peak ground acceleration. I just took one example of accelerogram. This is how it will look when how we save the earthquake data. It has a time, and this is your ground acceleration. They will not call always simply acceleration. They will say ground acceleration, because on the surface we have different acceleration. Building will have different acceleration. At the origin of earthquake, it will have a different acceleration. After 1 kilometer travel, it will be different. So we always target on ground acceleration, which means surface acceleration. I'll just go next slide. In this slide, I'll see that all these points are peak points. I just took what is the maximum point here in the acceleration. We call it as a peak ground acceleration. So this parameter is very much important for structural concept. So it's nothing. Whenever we get an earthquake, we take the maximum of the acceleration is called peak ground acceleration, which is always mentioned in meter per second square. So this meter per second square, we know acceleration will be meter per second square. So I'll just took this PGA. What I do, they don't want to mention in meter per second square. They like to mention in G. So 1 G is 9.81 meter per second square. So this we got from our Newton law, and he did a simple. We also in physics lab using simple pendulum experiment, we find our acceleration in our Earth is 9.81 meter per second square. So we say this 9.81 acceleration is 1 G. If I say 1 G means 9.81. So I'm dividing this by 9.81. So I'll get my peak ground acceleration in terms of G. Okay. So normally now it's very much famous. Whenever earthquake comes in TV, they will say Richter scale is 6, Richter scale is 5.5. So this is okay from the news TV point of view. Whenever the engineer talks, anybody talks, they jump to PGA point of view. Our code books will talk in terms of PGA point of view. They want to know what is the maximum acceleration happen. What is Richter scale says, how much amount of energy is released during the earthquake. That is converted to logarithmic scale, and that one they say in the Richter in terms of Richter scale. It's called magnitude. Then there is something called intensity, modified Mercalli. That depends upon how much damage coming to the building because of the earthquake. So we'll not go to there. For us, PGA is very important. In code books, all code books, they use PGA terminology. Okay. Next one is damping. So this is another important parameter. So what is damping? Damping is the reduction in the amplitude due to friction or internal absorption or crack develop, whatever it is. I am hitting my material, the material is undergoing deflection, and my deflection is slowly coming to the rest. So this isn't some example. When it is a 0.5 percentage damping, my building, this ash color, my building is, the structure is coming slowly to the rest. 5% coming, it's little bit better. 20% is far better. Okay. Now we always consider RCC member is 5%. Why? So many people done experimental study, and for concrete, RC, not only pure concrete, right? For RCC, it is 5%. If it is a steel structure, they say to use 2%. It will deflect more. It takes a lot of time than concrete to come to the rest. This is an
So is
example
it
for
2% or 20%?
no. This is 20% is some example, sir. Okay, example for this graph.
Okay.
Steel is normally 2%. Code book, each code book will give different near to this 2%. Am I right, Mr. Said, sir? Probably he escaped my lecture. Huh?
No, 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 I'm with you. I'm with you. No, no, I'm with you. I'm with
Yeah,
you. Yeah,
yes,
yeah.
sir. How can you escape? I will make you also
Uh,
to sit, sir.
yeah, the code
Sir,
says
what
it's
is the
five percentage of damping. The code says it's 5% of damping actually. That is a minimum requirement.
five
If you
five?
want to increase
Yeah,
it, yeah, 5%.
five for concrete, sir. For steel, how much?
Steel you can go for 2 to 2.5%. 2 to 2.5.
Yeah. So this, yeah. So concrete is code says concrete is uses say to use 5%.
Correct.
Steel is saying two, little bit higher, and again they increase with factor of safety. So much things will come. We will
Yeah,
say
I
in
would like to
randomly.
point out something. I'm sorry to interrupt you. I would like to point
No,
out
no problem, sir.
something. It's called like
Rest for me, sir.
torsional irregularity, as Dr. Haran mentioned. This is what we discussed in the last class. I mean, say for an example, it's a L-shaped building or curved building. I mean, now the question comes, sorry, is it a torsional irregular or not? I mean, it's again depend on the stiffness. I mean, if I do have more stiffness, I mean, the building is itself will control the torsion, isn't it? Actually, say for an example, if I do have flexible building, actually, instead of call it a stiff building, I do a flexible building as well. In the sense, what actually it is a lack of stiffness, but at the same time, it is satisfying the code requirements in terms of drift and as well as the time period. Let's move forward to check the further for torsional irregularity, because you're not going to limit your buildings to be checking only for the time period or drift or displacement, because you have to move on for the further checks as well. Okay, that we will see while you are doing the live model. But the thing is, now the question comes, I mean, so if the building which is under torsional irregular, you mean to say I cannot design torsional irregular. So whatever the building which we have, which we can able to see in a kind of different shape of building, I mean, 100% that is a torsional irregular, right? Actually, I cannot go and dump the stiffness. I cannot go on build the complete building as the shear wall, I mean to say huge stiffness, right? Actually, so you're going to spoil the architectural aesthetic view or even architectural utilities. In that case, I mean, you can design a torsional irregularity, but you have to increase this damping actually. So that damping is called, what do you call, I mean, the ratio between the delta average, which is delta max to delta average. So maximum displacement to the average displacement, if it is less than or equal to 1.2, then the building which comes under it is not torsionally irregularity check. Okay, it is not torsionally irregular. I mean. But the same ratio, if it is goes more than 1.2, the building comes under torsionally irregularity. Then what I have to do, whatever the result which comes, the ratio between delta max to delta average, then I have to multiply by this 5% damping to increase my safety factors. Then I will just go back again, further doing the analysis and design. So this will increase your reinforcement and as well as the section sizes, because you decided that you wanted to design with the torsional irregularity, isn't it? If that is the case, then you have to face, they have to add additional safety factors. So please go ahead. Yeah.
Thank you, sir. Yeah. So we'll see more about damping. So why we call there is something called damping: under damped, over damped, and critically damped. Uh, so I'll just try to what happen. Uh, so I'll just play this video. Let's see. I'll see. So they gave some example below. Under damped, what is happening? Critically damped, what is happening? Over damped. So under damp is going. Okay, the second figure is example for under damp. it moves on slowly, it comes to the rest. So it's called underdamped. The second figure is the underdamped here. Here blue color is the underdamped. Critically damping means, you see here exactly, so critically damped means it does not go one complete oscillation also. It starts, it comes to its rest position. So this is called critically damped. So let's say critical damp is 100%, which say within one oscillation, it not complete one oscillation. What is over damp is, you see this pink color in the right side figure. So it comes very slowly. My pink color is coming very slowly to the rest portion. So this is called over damping. There is another case which is called underdamped. Underdamped is not going to come to the rest at all. It keeps on going to vibrate. In practical, all the systems have damping, or due to gravitational force dampings are there. Now here is for our mathematical model, we consider this is undamped under damping condition. Now anyone in simple, I just shown this video. Maybe later we will share this PPT. You can understand what is under damping, critical damping, over damping. For our building point of view, all our buildings fall under underdamped system. All our buildings are fall under underdamped system. Then what is the purpose of this? No? So in some cases, in any machines or something, they use some gasket. Even they use some any free fall structure. They put some dampers below. Even in building, we have a dampers below. They think of this critical damping. Now they understood now under damped only our building is. We need to quantify mathematically. So to quantify mathematically, they compare this underdamped with critical damping. So this two we will be comparing. Critical damping means 100%. In within one oscillation, my building will come to one position. Underdamped means compared to critical damping, how much oscillation it takes to come to its original state. That is, by comparing, we will say what is the damping ratio. So I'll go back to this slide now. So it's loading. Huh? Yeah. So what is this damping ratio says that is the ratio of actual damping to the critical damping. So critical damping is 100%, which means within one oscillation, my damping has come. C means this is the actual damping for the structure. This ratio called xi. Now mathematically, critical damping we can found using this formula 2m omega n. Omega n is what? Your natural frequency, which is k by m. So if you know the critical damping, they substitute here in this formula. This formula can be rewritten like in this formula. We should know what is xi. Okay, so this xi, our code book is saying they found this value experimentally. For RCC structure, they say to use 5%. Okay, so they use 5%. They get the damping for C matrix, C for the our structure. This is the C. Again, there is something up. All these formulas are applicable for single degrees of freedom system. Okay, whatever we find, all these are single degrees of freedom. Then we will see how they are using in multi degrees of freedom system. Now I think everyone clear, right? How do we find damping? What is damping? Mathematically, how they find damping. Then this is another way to find damping also, called logarithmic decrement. This is how they used experimentally. They pull the structure, they leave it, and they with number of cycles you get the how much is the amplitude. So we will find logarithmic decrement, delta called logarithmic decrement, ln of x1 by x2, or suppose ln of x1 by x4, we divide this by 1 by 4. This we get the logarithmic decrement. So once you know the logarithmic decrement, you can substitute in this formula. We'll get this also. They further simplify this to simply 2 pi xi. Okay, 2 pi xi only they use, because if my xi value is less than, we are going to get less than 0.1. because concrete is steel is 5% means how much? It is 0.05. Steel is 2% means how much? 0.02. If you substitute this value in this xi, this is denominator value is going to come. Again, we are doing square root. It's going to come 0.99 or 0.95. So we remove this one. We just use 2 pi xi. And this is also another equation we can use. All are same. So we can find from by experimentally we find logarithmic decrement. From the logarithmic decrement we can find xi, and this xi we will substitute here and we get C for the system. Then another important is stiffness. Here stiffness we know it's the ratio of load divided by deflection. But what I want everyone to understand here is, in case of seismic, my stiffness is, there can be so many types of stiffness. When I apply axial load, my axial load divided by axial deformation, this is called axial stiffness. Okay, so this is called axial stiffness. Similarly, I will apply a load here, and how much is deflected here. So this is called bending stiffness. Okay, this is called bending stiffness. Normally for column, it will be 12 EI by L cube. Normally we take, but this is not correct. We analyze from software. Normally stiffness. Suppose I will not apply one force. I'll apply moment here. Okay, I'll apply a moment here. One moment or some moment. Then this will undergo some theta. This will undergo some theta. So I will find stiffness related to theta. And also I will apply one torque. I'll apply torque in the top. Suppose this is the top of the column in the plan. I'll apply the torque. How much my theta is deflected. So we will find the torque stiffness also. So there are so many different types of torque available. But in case of seismic, we are going to consider my degrees of freedom is only in this axis, x-axis. We will not worry about all other stuff. Of course, our MATLAB, what is that? Not MATLAB, StatPro will consider everything. Mode shape will be developed, but our codebook formulas, equivalent lateral load method or response surface method, even our response spectrum given in the code is only for x-axis. Okay, is only given for the x-axis. So we will be using only this stiffness. What is this stiffness called? Bending stiffness, or you can say lateral stiffness. Lateral stiffness is correct. Because I'm applying the load laterally, I'm finding the stiffness in the lateral direction. If it's a beam, I'll apply the beam here, how much it is deflected here. If it is or in the midspan, how much is deflected. So stiffness is an important parameter. Then next one is coming mass. So mass is the very important, because we all know how much force is going to develop. It depends upon mass into acceleration. This acceleration we know, earthquake acceleration and mass is self weight of our building. Usually we go for lumped mass system. This is UX direction. This is what E.T.A.B.S will do. It will assume our mass in X direction, Y direction, even in the rotational axis. This is actually beam element. If you know, again, FEM is required to understand here. This is a beam element. You will consider what is U, V, and theta. This is two-dimensional beam element. Lumped mass will be developed like this. There will be a three-dimensional lumped mass will be there, where you have a U direction, V direction, and Z direction. Theta X, theta Y, theta Z will come for one node. So there will be two nodes. So matrix size will go 12 cross 12. I'll not confuse this here. Maybe later stage, if I'm teaching you FEM part, will make you understand more. What this consistency mass is saying is, because of this also, this node also the mass effect will come. Because of the mass in X direction also, the mass will in Y direction also, the mass will come and sit here. This is the more accurate method. But in case of seismic load, since we are considering only the x-axis, this is enough. When we are modeling for rigid diaphragm, when we are modeling some rigid diaphragm like a slab element, then to get more accurate answer, they go for consistency mass for different kind of application. for generally for buildings with seismic load, where we are concentrating only in x direction, we consider this a lumped mass. We'll go to the mathematical model. I'm just mathematical model. I just took one frame. We have a one frame, and one frame has some slab, and this slab has a f of t. Sir, how you all are feeling, sir? Boring, or is anybody feel like I want to finish the class now and continue next class? I have more 65 slide. Huh? I am in the 50-second slide. How you are feeling, sir?
Sir,
We'll
Mr.
continue.
Suresh, Ammar, Mebin, Rohit, is that been okay, or how it is? I mean,
Yeah, okay, Mr. Syed, actually, it is fine.
It is
yeah.
tough,
Yeah,
but there is no other way to go, like what Sai sir says.
No, actually, I think whatever it is there, I think we have to go through once after the PPT is received. So we will go through it, and if it is any clarification is required, maybe we will interact direct, means face to face also. That will
So
be,
for sure,
yeah,
mm,
yeah.
it is
Fine.
our pleasure. I mean, whatever the question which you do
yeah,
have, I mean, you can, point out even while you're go through. I mean, just put a voice note in your WhatsApp, and then you will not miss this. Actually, you can take the same voice note and the class. Actually, you can just, what do you call, recall it all your questions. I mean, get back to us. We will answer it for sure. Because the reason
yes,
why we've been discussed with Dr. Haran, actually. I mean, he said, like, I'll directly take to the problem. Then we concluded, actually, if you directly take to the problem, then it will be like, some of lack of information which you are missing. I mean, if you don't teach in a bit of basics, I mean, nobody can understand. Again, you're going, like, in the formula basis, actually. So that's what we requested to go into the. I understand. I mean, it will be like, little boring, but you need to digest, because this is very basic and very important. I mean, if you don't understand, then there won't be any point out, like, to go for further analysis, which you are going for, like, the single mass or double mass, three mass, in order to carry out the, like, full concept. Yeah, please go ahead.
yes, agree,
Thank you, thank you,
agreed,
thank you,
agreed.
sir. Yeah, yeah. Yes, sir. You have something to say?
No, 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 agreed. I am agree, 100% agreed with Mr. Syed.
Okay, okay.
Please go
This
ahead, sir. Please
it
go ahead,
looks
actually.
like dry, but once we understand the concept, we'll feel easy and happy.
Yes,
Let's
yes.
go, sir. Yeah. So I just took one
Yes, sir.
frame. Yes, yes,
Sir, please go ahead. No worries,
yeah,
please
yeah.
go ahead.
Yeah, I
Okay, sir.
agree
Okay.
with you.
So yeah. So we have columns here. Actually, two columns. One beam element is there. What we are doing is, for simplicity, we consider this both the columns is joined together. We will design like a equal stiffness. We will design it has some. So this will be designed like a one column which is having a effective stiffness of both the column, which is model which is having only in x direction, and this mass will be lumped here. That is called lumped mass. And by nature, because of the internal friction, the damping will be present in this column. So we call this damping as a C. And the F of T force is applied. The force, they write it like F of T. Yeah? So F of T means my force is changing with respect to time. So this is the idealization of my model. This is your actual. Already we idealized. This is not actual model. We idealized. We designed what in theorem of three moment method or slope deflection method. Frame analysis will be represented numerical model. This one. So this numerical model, for understanding purpose, further is simplified to 1 degrees of freedom system. This is very important. Now, why I am calling this as 1 degrees of freedom system is, I have one mass. This mass is going to move only in this x direction. That is why we call this as a single degrees of freedom system. Suppose I have mass. Suppose I have a two mass. This mass is moving in x direction, this mass is moving in x direction, then we call this is a 2 degrees of freedom system. Okay, suppose I have another example. We have a mass. This mass is moving in x direction, this mass is moving in y direction also, this mass is moving in z direction also. Then this, even though it is one mass, it is moving in three direction. This we call 3 degrees of freedom system. Okay, so we have to understand What is single degrees of freedom system, multi degrees of freedom system? For our codal procedure, using let's say for our simplified procedure, we go only with this. We go only with this. But when we are doing it in the E.T.A.P.S, we go actually per node 6 degrees of freedom system will be considered. Okay, per node 6 degrees of freedom will be considered. Then only the torsion mode. In this case, you will have only bending mode. You will have only the bending mode. If you consider all the degrees of freedom system, then only we will get different bending modes. So I'm not confusing much here. We will say mass is there, the mass is allowed to move only in one axis, we call single degrees of freedom. We decode this further. So this single degrees of freedom, this is called mathematical model. This is very simple model. Why they say this one? First they draw this mass. My mass is, why they put a mass as a box. This is my rigid. My mass is rigid. It's not going to deform. It's not going to deflect. My mass is going to, this mass is going to move in x direction. So they put a wheel here. So if it is like a roller support, this is going to move in x direction. When it is going to move, when I apply a force in of f of t, my mass is going to move in this direction. Now, when the mass is applied in this direction, who is stopping my mass? Who is stopping my mass? The stiffness in the column. Here we saw the column has a stiffness. The stiffness. The who is stopping my mass? The stiffness is stopping my mass. Again, who is stopping my mass? This damping is stopping my mass. Okay. So this is the simplest representation of mathematical model, and here they make a fixity. Now again another thing, when the force is applied, the inertia force is also developed here. Okay, that they will not write here because it's by default understand because of this marks and this x. Which direction it is applied, in that direction only it will be moving, and in that direction only inertia force will be developed, but inertia force will be developed opposite to the force applied. So what they try here is, uh, when the applied force is developed, we have a stiffness force, we have a damping force, we have an inertia force. All my force is taken by these three forces. What is this F by I? We call mass into acceleration. My acceleration is changing with respect to time, so T is coming. So this is my inertia force. This is my damping force, C into velocity. Velocity, C into velocity is my damping force. K into T, K into del. This is my stiffness force, which is equal to P of T. What is the beauty of this equation? This equation is called dynamic equilibrium equation. Okay, this equation is called dynamic equilibrium equation. What is our static equilibrium equation? My static equilibrium equation is, if my load is applied, it's going to deflect. If deflect, I have a delta which is x. I will be not having velocity. My velocity is 0 here. My acceleration is 0 here. My force is not changing with respect to time, it's P. So ultimately, we get P is equal to K into delta. My delta is not changing. So this is my dynamic equilibrium, static equilibrium equation when my dynamic equilibrium is when there is no velocity or something. So this is this equation they derive from D'Alembert's principle, energy equation, the Duhamel's integral. They solve this. There are different methods. Rayleigh-Ritz method. They use Lagrange's equation method, energy method. We will not go to that much. So this is how simple. Actually, this looks like D'Alembert's principle. When the force is applied, three forces will be developed. What all the three force? Inertia force, damping, stiffness force, damping force. When my force is not changing with respect to time, velocity and acceleration is 0, we end up with static equilibrium equation. Sorry, not in the show. Yeah. So next step, We found now this is our forced vibration equation. Forced vibration equation. How my building is behaving under earthquake, we need to solve this equation. If bomb is blasting near to the building, I apply the speed. I need to solve this equation. This equation how to solve in analytically, we say complex integral and particular integral, pi x of ct plus p of I, pi particular integral, p of I. Analytically we solve like this. Or in numerical integration method, there are different method is there. Newton-Raphson method, Hilbert-Hughes Taylor series method. They assume this all approximate method. Analytical method is accurate. This is required to identify how much my member is subjected to the load, how much it is deflected, how we will find. So this method is very difficult. So code is simplifying to use it under earthquake. Even when they are modeling a high-rise building, they have to model this. They have to do this, and they have to find what is the maximum values coming. Any important buildings, they will do for this. For example, let's take Burj Khalifa. I'm sure for Burj Khalifa, they would have done the nonlinear analysis for this equation. Without that, they will not construct the important building. They do this procedure below procedure, but finally they take the decision based upon this forced vibration analysis. Now in the forced vibration analysis, because of this damping because of this damping is taking some force. So for conservative point of view, because modeling damping is very difficult, they go for global damping. Local level modeling damping is very difficult. Numerical modeling, for example, you say reinforcement, the column reinforcement is different in different location, so obviously the damping behavior is different. If you go to the element level, we can model it as a global damping. Normally they use Rayleigh damping. They call Rayleigh damping is a function of mass matrix and K matrix. They use alpha 1, alpha 2. This all the higher level. I'm just giving the glance. What is that? I don't want to confuse you here much. I'll just erase all. What they try to do here is, for a conservative point of view, they say my all the loads are taken by mass and K only. I don't want to consider the damping system at all. Then it is called undamped force vibration. Okay, so undamped force vibration. When I see this displacement profile, it will be like this. It will never come to. It will never come to this. It will come some part because of this k into this part. Because of this also some part it will come to the solution, but it is very less. The more is on damping. For mathematical simulation less point of view, they use underdamped. What is undamped force vibration is, undamped force vibration means they don't consider C. Damp free vibration is what they do, they ignore the force, they just initiate the damping, they do this one. This kind of analysis is where they do. If they in buildings they are not doing this, but for sorry, what happened in buildings they are using it. uh, but let's say let have a aeroplane wing. So let's say aeroplane wings. So this wing is carrying engine. So when this engine is carrying, I have a frequency. Applied load is there. So under free vibration, they go for this kind of equation. One practical example. Not only for the wing, they go for the whole system. Anybody felt that one when we are sitting on the aeroplane, when they pass the clouds, we feel the vibration. The people who sit near to the wings, they get less vibration. The people who sit near to the tail, they get more vibration, because this point is like a fixed cantilever. So here it will go more deflection, and here they go less deflection. Whole body will also have a vibration, and this part will have more vibration. So they consider this. Then then there comes a famous, for our civil engineering point of view, is undamped free vibration. We will not consider C also, we will not consider f of t also. Using this equation, we find frequency, we find the mode shapes, and then we use this value to find this forced vibration. Okay, we are whatever we are finding is not the final one, huh? We use this value and then we jump this value. This is called simplified method. We use simplified method. So simplified method is, I am first consider it is in my system is undamped system, then I will use this mode shapes and frequency value. I'll use it in this equation. I think I'm saying the same, huh? I'll just go to the next slide, huh? So what they do, this is our natural frequency, sorry, this is our mode shapes, sorry, undamped free vibration equation. uh, we have some equations, we find eigenvalue, eigenvector. For this we'll find mode shape. Let's say this is my 4 degrees of freedom, each mass is moving only in x direction. A mode shape is a specific deformation pattern that structure undergoes when it vibrates at its own natural frequency. Now here I will come to the natural frequency. What is natural frequency is, according to the equation, my omega equal to root of k by m. If you find this, this is your natural frequency. Okay. What is this k? K is the stiffness of my actual building. M is the stiffness of my actual mass. Okay. There is two things we need to find: natural frequency. There is something called damped frequency. Yeah? Damped frequency. What we are finding experimentally, I go through my previous slide now. It's loading. Yeah. I think first slide. Yeah. What we are finding here, no, the frequency in this manner experimentally, we are not finding the natural frequency. We are finding that damped frequency. Yeah, we call omega d. Omega d is equal to, some formulas are there. Omega d equal to natural frequency divided by 1 minus something. I forgot. Minus 1 by xi square. Okay. So omega d equal to omega. So this natural frequency means ignoring the damping system, how only because of mass, only because of stiffness, how much my system is vibrating. That is called natural frequency. Because of this. Yeah. Okay, now we know this frequency. Now, when we solve this equation, when we solve this for 4 mass, you get 4 frequencies, W1, W2, W3, W4. What is this frequency meaning is, this has some number. Let's say some 4 radians per second. If you solve this, when I apply a 4 radians per second at this location, some load like this, exactly like a frequency, I apply 4 radians at this location, this system will undergo deflection like this. Okay, exactly like 4. Let's say this is coming 8. If I increase this frequency to 4 to 8, my system will deflect in this mode shape. So mode shape is what? Is a deflected shape of my structure for a particular frequency. For a particular frequency, let's say this is a natural mode shape. Uh, Sir, I think I'll just take some 2 minutes rest. Is that okay? I'll just take 2 second rest. Like a break
No,
will take.
no, no,
Sorry,
no, no. Yeah.
2 minutes. 2 minutes break. Yes, sir. Yeah.
Sure.
Hi, all of you. How was the class? I mean, how do you felt actually?
It is nice. It's more theory, so we're just trying to understand the concepts explained by Dr. Haran.
Again, like, because while he was going for the examples, like, worked examples, then it will be more clear whatever he been, like, talking about in terms of mode shapes and degrees of freedoms, and this m of x plus k of x equal to 0. Yeah, I think Dr. Haran
Hi, sir.
come
Yeah, yeah.
back. Yeah, okay,
Hi, sir.
okay, move
I'm back.
forward.
I'm back.
Yes.
Yeah, yeah,
Yeah, yeah.
please.
So, yeah. So where we are, sir, now, mode shapes. Now, sir, mode shape is a deflected shape of my structure for a particular frequency. Each frequency has an associated mode shape. So in this example, we saw all the bending mode shapes. Huh? We see all this is one side bending, this is both side, so this all associated with bending mode shape. Why we are not getting here torsional is because my stiffness matrix is derived, or mass matrix is derived only for the horizontal force, only for the x-axis. Next step, I'll just go how we find one small example. In next class, we will do actual example of how to calculate the mass matrix, how to calculate the K matrix for actual building, and how to find the mode shapes and frequency. And from the mode shape and frequency, how to find the base shear force. So this we will see in the next upcoming classes. Now let's take this small example. This is a 3x3 building. For example, let's say this. I have a mass, E mass. uh, we have this mass is 8 here, mass is 8 kg, 8 kg or 8 ton here, 4 ton, irrespective. And this is my K, this is K effective. K effective here, K effective here. So this K is also somewhat differently we need to calculate. They need to take K1 plus K2 to get the effective at this bottom. I will say this later. Now, how to develop this mass matrix, K matrix, we'll forgot. We'll do next class. Now, mass and
Dr.
K matrix is
Haran,
given.
I'm sorry to interrupt you. Are you going to take the example, worked example now, or just a glance?
Sir, this is a small example, sir. 2 slide, finish.
Okay, because I would
Mode shape.
request, like, what do you call, because this worked example, we can take it to the next class actually. What do you think, Ami? Because worked example
Okay, sir.
will be like, while being like, going for the worked example, then they will only concentrate on the examples. Because now for some of them they do understand, but some of them actually they need to, like, go through your PPT, which is like, which you're going to give us study material. Then let them go through it. Then
Okay.
when you're taking the example, I'm 100% sure they will understand.
Okay, sir. What is the time now, sir? That's why, yeah, already
Almost,
late, huh?
yeah.
We are.
Yeah, 9:25. Yeah, correct.
Hey,
Yeah.
9:30. Sir, I took a lot of time. Sorry.
No, 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 it's fine.
We
It's
are.
fine. No, no worries. No. So is that okay, or do you want us to continue the class for the worked example as well for all other?
Sir, they feel bored, sir. I know. We'll
Yeah,
postpone to next
yeah,
week, sir.
yeah. That's
They
what.
will
That's
be.
what. That's what. See,
No,
Already.
actually,
anyhow,
no,
yeah.
sorry. Actually, it's not a boring, but since it is a theoretical is there, so if it is, I think it's better to glance it once, so it will be more effective when we are having this example in the class.
Correct,
Yeah,
exactly,
yeah.
exactly.
Yes, yes.
Yeah.
Yeah.
So we will circulate the study material. So let them go through it. I mean, and if possible, we'll discuss actually. We'll try to circulate the soft copy. I'll see actually how we can best in this. I mean, because we can just formulate this PPT, and while you are circulating, I mean. And moreover, thank you so much. Thanks for your attendance. I mean, so hopefully the lectures, which is very fruitful. Even I really enjoyed actually, because it's completely, he's recalling my complete masters. The whole IIT complete masters he was recalling actually. That's fantastic. I mean, really, I mean, I would feel actually all or enjoyed the session which has been given by Dr. Haran, I
Yeah.
believe.
Just one thing, what I want to
Yes,
update, no,
yes.
sir. I just skipped so many things, sir. How the
Yeah,
formulas came, all the concepts I want to give,
that's
but
fine, sir.
I don't know.
Even we don't
Uh,
need, actually. I'm telling you, to be honest, actually. Even
yeah, true.
nobody
That
needs
is true.
how the equation has been, like, if you're giving the
Uh,
solid concept and understanding and moving forward for the worked example, then it will be very clear for us.
mhm. Fine, sir. Fine.
Yes,
Thank
sir.
you all,
I
sir.
to feel once we do some examples, maybe the concept will be more clear.
Yeah, that's
Yeah.
what
Yes,
I
sir.
told you. Because see, if you directly go into the examples, I'm 80% sure, maybe 20% you may understand, but 80% it will looks like, the confusion part only whenever you use the terminology. Now, what happened? He showed so many photos, so many examples, and the bit of couple of equation. Now, if you move to the worked example, I mean, I'm 100% sure. I mean, you will get it, like, with the help of concept. The once the concept is very clear, khalas, actually, then while you've been, like, taking the stat, even the e-tabs, actually going for it, when you have been extracting the drift and displacement and torsional irregularity check, actually, and extracting the moment, extracting the base shear, extracting the weight of the structure, then it will be, like, very easy for you to understand those terminology.
Sir, I just want to share them just a glimpse of next PPT.
Yeah, for
Uh,
sure, for
just
sure,
I'm
for
just
sure.
sir, I'll just share my screen one more time.
Yeah,
Let's
yeah,
see.
please, 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 please.
What I have in the other PPT is this. Yeah. So what I have other PPT, some again difference. Then I'm going this response spectrum. Then how response spectrum is developed. Then from codal side, how we will from codebook A.E.X.L codebook, how we take using equivalent lateral method, how do we develop the forces. So this is what we need exactly.
Correct,
Uh,
exactly. This is what we
yeah,
need
so
it, actually. This is what we need it.
uh, directly I can jump here, but we will not understand here what is this CS, what is time period, how this formula came. All this we will not understand if we jump here directly. So this session might helpful for that.
Fantastic, fantastic. We'll discuss, actually, how we can deliver
Yeah.
in a very fruitful. I mean, then we'll just, deliver accordingly. No worries.
Thank you, sir. Thank you all. Yeah.
So thank you so much.
Thanks,
Thanks
sir.
for all. Thank
Uh,
you so much.
Thanks all.